Hello world, welcome back to another tutorial. Today we're going to be talking about instanced model rendering, which is basically the idea of instead of rendering, the same model over and over and over and over and over again, we're going to take just basically one copy of this model and reuse it over and over again. So we're only going to be doing one draw call as opposed to however many draw calls it would take to render that same exact model. And we'll get more into exactly how that works in a second. It's pretty cool. It's going to optimize our system to be able to draw a lot more objects. But before we get started, just want to let you know, down there in the description, I have left a link to the code on my GitHub. You can go clone that or download it, whatever you want to do. That's going to be the end of this episode. So that's going to be the code, the finalized code. If you want last week's code, you can go ahead and just go to the episode before this, grab that code, and it'll basically be the starting project for this week's code. So I suggest going and doing that if you want to follow along and kind of code along. But other than that, let's get into some model rendering because I'm pretty pumped. All right, just like always, I want to talk a little bit about what we're going to do through some keynote presentations. Let's talk about instance model rendering. Currently, we have our cube mesh, which consists of two different things. One being the mesh. The mesh is basically the vertices that are on there. So if we look a little deeper, we have 8 vertices. Each one of those vertices is 16 bytes each, which comes up to about 128 bytes in total for just the mesh that's attached to our object. The second thing we have is model constants. Now the model constants are the position, the rotation, and the scaling, as of right now, of our mesh. Okay, so when we rotate, change the position, or scale it, that all goes into our model matrix. And our model matrix is 64 bytes in total. So for every single cube that we draw on the screen right now, it's about 128 plus 64, which is 192 bytes for one model. Okay, so if we wanted to render an entire scene of cubes, what would that look like as in the current scenario that we're rocking right now? All right, so we have 27 different models in this scene that we've added one at a time, each 192 bytes. That comes out to about 5,100 bytes in total that we're storing for just cubes on our scene. Not too bad, okay? It's not too bad. Can it be improved? That's the question. Okay, so let's just store this 5,100 bytes up at the top in our not instanced little purple or pink box. Okay, so our memory is 5,100. Now, let's talk about our render function in each model. So for every single model, we are calling render, right? So the first thing it's going to do is it's going to set the render pipeline state. The render pipeline state's in a library. We don't need to worry about the render pipeline state because it's already been generated. We just need to grab it. So it's basically just one quick grab call. We need to set the vertex buffer. Every model has the mesh and then mesh.vertex buffer. It's attached to it. So we're just going to set the vertex buffer and we're going to set the model constants for that mesh too. So for every single model, we're going to have a vertex buffer and model constants attached. Then we're going to do a draw call. Now let's focus a little bit on this draw call. And for here on out, I'm going to use this pink D to represent the draw call. Okay, that pink D, son. So yeah, let's take the 27 different models that we have on our screen right now in our scene, and let's talk about what's going to happen. So for every single one of these models on the screen, we are going to draw them, right? Because every one of them has the render function, every one of them has a draw function. So we're going to set the vertex buffer and the model constants every single time we render. So let's take a look at what that looks like from an overhead perspective. So right now we have our CPU and our GPU, and we have our 27 models in our scene and our draw function, right? So if we want to currently draw right now, we draw one at a time, okay? We're just going to draw one at a time because we've added these, like the same exact copy 27 times. We're going to draw every single one until all of them are on the GPU, and then it's going to render onto a texture, okay? Actually, what's going to happen is it's going to send it back to, so when we call draw, it's going to go to the GPU, and then it's going to come back, render to a texture, and so it doesn't really stay on the GPU, but let's just ignore that for now. So one at a time is what I want to get out of this one. So that's 27 different draw calls. Okay, so I'm gonna take this 27, I'm gonna store it up there and call it draw calls. Now, let's talk about instance rendering. Instead of taking 27 different models of the same exact color and everything's basically exactly the same, instead of having the exact same mesh for every single one, why don't we just use one? Why don't we just use one mesh, which is 128 bytes, and we'll just use that as the skeleton and have 27 model constants, which is the rotation, the positioning, and the scale in an array, and then, use the mesh. So we'll render the mesh and we'll just use a new model constant. So what we'll have instead of 5,184 bytes is 1,728 bytes plus 128 bytes, which equals only 1,800 bytes. Okay, look at that. Boom. Just from going from non-instance to instance, we have saved a lot of memory. Okay, so let's talk about the draw calls. What does this mean now? All right, so we had our 27 models before. Now we only have one, and we have 27 model constants buffer. So instead of having a mesh for every single model on a cube model, we're gonna have one cube model and 27 model constants buffer. Okay, so how many draw calls is that gonna be? One draw call. That's all we need now. So instead of 27 different draw calls, which is a bottleneck in graphics rendering, we only have one draw call now. Wow, look at those numbers. They kind of speak for themselves. I mean, 5,100 is a lot bigger than 1,800, and 27 is definitely bigger than 1. Okay, so, I mean, right now we're only rendering a cube, but could you imagine if we were rendering one of these things that have a lot more vertices? If we were sending 27 of this woman with very defined features, 27 of her to the scene, and also her model constants, I mean, it would be huge. It'd be such a big memory difference. So instead, we'll just store one woman and a bunch of her model constants, which is basically whatever the size of the model constants is. Or even the armadillo, which I'll probably start using later on in the series. But yeah, I mean, it just kind of adds up. So where could we actually use this? Well, a really common place to do is grass, right? So grass is a bunch of different models on the scene that are kind of waving in the breeze. And what we could do is we can create grass instance models that store, it's like one object that stores all of the different objects. And instead of rendering, this is 5 by 6, so that's 30 and 30 and 30, so that's 90 different nodes that we would have to add. Well, instead, which is 90 different draw calls, well, if we instance it, it's only 3 draw calls for all of them. And then each grass instance model could be a different type of grass. So we're saving memory and we're saving draw calls, which is huge. And I'll show you exactly how big of an impact this actually has in our code right now. Okay, before I actually get started with coding, I've already coded all this. I'm not gonna go back and delete everything, but I do wanna kind of point out to you the draw calls. I didn't actually mention that in the video, and I think that's super important. So if I run the scene with just a lot of objects on the scene, you'll see we have this nice little cube set up. But if I click on this camera icon down here, and I can see more like rendering stuff. This is how you like debug on the GPU, right? You'll see over here, like all the draw calls for those objects is crazy. Like, look, draw primitives, every one of these is a draw call, and it's just, they go on and on and on because every single object on the screen needs to draw everything. So let me just clean up this code and get to the end of this episode and show you what it'll look like afterwards. All right, so I've went through and I've kind of cleaned up the code a little bit, and right now we're rocking 46 frames per second. That doesn't really have anything to do with my computer or with like this. It's just I'm running ScreenFlow. It's taking a lot of processing power, but ignore that for now. And let's go look at the GPU now and see what the draw call. Look, this is it, one draw call. All of those other draw calls have been eliminated. We've just basically replaced every single one with one draw call. So I thought that would be pretty cool to show you guys. Everything's kind of just stored now into this one model constants buffer that looks like this. But yeah, super cool. I just didn't point that out, and I think you would think that was interesting. So let's go. All right, rocking the new Xcode dark theme. Am I right? Yeah, go Xcode 10. So yeah, let's look at our sandbox scene. Let's start with our sandbox scene, okay? Because this is where we're rendering all of our objects. As of right now, if I were to press play, we have, what is that, 16 by 10 cubes rocking, rolling around, all that jazz. And that's coming out to be about 60 frames per second. Now, that's awesome, but say we wanted to add more of these on the screen. So what I'll do is I'll go into our add cubes. I'm gonna create another little for loop. Z in negative, let's do 20 ... less than 20, like so. And then I'll take all of this logic and put it into the Z. So I'm basically just gonna create the cube in the Z. So this will be the forward and back. So we're just gonna basically add some depth to our cubes. And in fact, I'm gonna make it so up and down, it's 20, 20. This will be 20, 20. And Z will be 20, 20. So 20 up and down, 20 left and right, and 20 back. Okay, so that is actually 8,000 objects. Math, right? So we want to add 8,000 cubes rotating on the screen. We're going to need to copy let position X, paste that into the Z, and we'll just create position Z equals float Z, and cube.position.z equals pause Z. Cool. And then, yeah, we'll set the color. We'll set the random color. Oh, my camera's position, we'll want to move that way back. Since I'm adding depth, we're going to want to push it backwards a little bit. And let's press play. And hopefully my computer doesn't blow up. Yeah, odds are it does. So, yeah. Wow, if you ran this on your computer, it's probably just as slow. Maybe not. Maybe you have a sick graphics card. Just up those numbers a little bit, and it'll break. It's not broken, really, because over here you'll see it says 3 frames per second. And yeah, this is not a very exciting game atmosphere, if you ask me. And if we remove all of our cube set colors, I mean, it still runs exactly the same. And the reason I'm removing the cube.set color is because this is supposed to be about instancing and the same copy over and over again. So same copy and over again still runs at 3 frames per second. Let's fix that with instancing. Okay, so first thing I'm gonna do is I'm gonna go down to my game objects. I'm gonna create a new file, and I'm gonna call it instanced game object. All right, so the instance game object is gonna be a lot like our game object class, a lot like it, very similar, except it's going to be instancing things. So let's do some import of metal kit up at the top. Class instanced game object. And we're gonna inherit from node because just like game object, it is a node. Instance game object is a node. And then we're gonna want to extension on instance game object as renderable so that we can render it to the screen. This will need a do render, and we'll implement that in a second. And the last thing I want to do is also make it so that we can create some sort of a texture for the main clone. So I'm going to copy this material properties from game object, go over to instance game object, and just paste it at the bottom. But we need a material. So on here, I'm going to create a public, well, let's just make it a var material that will equal material. Okay, so easy peasy. Nothing should break. If I were to build it, everything works. Not right. Right, because this says extension game object. Since I copied it over, we need to extend instance game object. Everything should be just fine. Nothing's gonna break. But we do need to make it work. So how do we make it work? Well, instance game object is made up of 2 different things, okay? It's made up of var nodes, and we're gonna make these private. So private var nodes. The nodes is basically what we're gonna be updating that has the model constants attached to it. Remember how I said 27 different model constants? Well, that's basically, we just need an array of nodes. So let's create an array of nodes here. And the second thing we're gonna need is private var underscore model constants. Right? Yes, because we're gonna need to create a buffer of model constants. So this model constants is basically going to be a replica of what's in our nodes. And I'll show you what I mean in a second. Hopefully you'll be able to read into it a little bit better once we create our functions. Let's create an initializer here. Actually, above here, let's just create a new just so you can kind of see it a little better before we get into the initializer, let's create a private var model constant buffer. And that will be an MTL buffer. So all the contents of model constants will be put inside of this model constants buffer. And then we'll update every single one of these model constants from our nodes array. You'll see. We're going to pass in the mesh type. Mesh types. And we need an instance count. And this will be how many instances of this we want to make. How many copies or clones do we want to make of this one mesh? So we'll pass in one mesh type. That'll grab our mesh for us, which is basically our vertices. And then however many of those we're going to need to instance. So let's instantiate this stuff. Super.update or super.init. My cat's over there taking a poop in the litter box, so if that's what you hear, that's what it's doing. We're going to go super.init, that's fine. I'm going to create a new function underneath called func_generate. And what that's going to do, I'm going to call it generate instances. And then I'm going to pass in instance count. Int. And this will generate these arrays up here. And that's all I want to do. I want to populate these arrays. So I'll do for underscore, because we don't really need a variable. We just need 0 ... less than instance count. So for every instance count, every instance that we want to make, let's make it. So let node equal node, let model constant. Well, really, we could just go nodes.append node. Model constants.append model constants. Right? And really, we could take this guy, put him right there, so it'll look a little cleaner. Boom. From the top, we'll call self.generate instances, instance count, pass that through. Calling that function. Now that we have our model constants array filled up with however many model constants we have, let's create our buffer, our model constants buffer. So func, we're going to call this create buffers. And you can call it create buffer, but I'm going to call it create buffers because what if we want to add more buffers to update in the future, like an array of materials or something? 0 ... less than for this in. Don't forget the in. Yep. So up here we're going to call self.create buffers, and we'll also want to pass in the instance count. So I'll pass in the instance count there, copy this instance count parameter, and just put it in there. So in create buffers, I'm going to go model constants buffer dot, let's say, no, yes, equals engine. Let's grab that engine stuff. Engine dot device dot make buffer. And we're not going to pass any bytes right now. We just want it to be a certain length. So when you say make buffer of length, it's basically going to allocate space. And in that space is going to be model constants. Like in our case, we have length. Okay, what does that mean? Model constants dot stride of however many we want. So instance count. So we're going to create 27 slots or however many slots. So if the instance count is 5, we're going to create 5 model constant slots in a buffer. Then we can just update that buffer over and over again. And the options, I'm just going to pass in an empty array. So let's create this empty buffer of model constants.stride of however many instances. Okay, so hopefully that made sense. If it doesn't, hit me up in the comments. I'll answer any questions you have for you. So now that we have this model constants buffer, and we've generated our instances, let's go ahead and update this stuff. So func update, we're just going to override this actually. So this is this func, if we just type update, I think right here. Yep, override func update. And at the end, don't forget to call super.update. Yes. All right, so we have all of our constants. We have all of our nodes. How in the world do we update our model constants to replicate what our nodes did? Well, that's going to take a little bit of new knowledge. All right, so I'm going to type this out. Let pointer equal. Let's grab our buffer. Model constants buffer dot contents. So that's going to return the buffer contents. okay? So our buffer was generated from an array, but to inversely go back and grab that data, what we're gonna need to do is we're gonna need to grab the contents of our buffer. Dot bind memory to model constants dot self. Capacity, what's our capacity? It's model constants. Oh, well, let's use, let's do model constants dot count. So what we're doing here is we're literally grabbing the contents of our buffer and we're binding that to this pointer. So this pointer is pointing basically at the very first, it's the first value in our buffer, and then it goes up to the end of our buffer. So pointer can be used very sophisticatedly. So the next thing we're gonna do is we're gonna create for node in nodes. Remember, if you have questions about this, ask me in the comments, go to the Discord channel. I will answer your questions. This is a little bit advanced, but hopefully you're getting it a little bit. So for nodes and nodes. So basically what we want to do is our pointer is our what we're setting up to the GPU, right? So we can say pointer.pointy.model matrix. You see, pointer.pointy is a freaking model constant. You see, if I go right here, right there, it's a model constant because it knows that I'm binding to model constants.self. Pointer.pointy is a model constant in our buffer. And I could set that model matrix equal to, well, the node.model matrix. So I'm updating the model constants buffer, the actual value. I'm gonna set this to var, by the way, var pointer. Pointer.pointy.model matrix equals our node. So whatever node we updated in this array, we can set that value right here. And then so that was the first model matrix. Now we want to get the next model matrix on the next for loop iteration. We can say pointer equals pointer.advance by 1. So that's going to go one more index to the next model constant, and that'll grab it for our next node, and then we'll set that model matrix of that node equal to the node model matrix. So this is us updating our buffer. Okay, so our buffer has already been made. We don't need to generate a buffer every time. It's expensive. We can just update the values in our MTL buffer on the fly. So this right here is going to do that for us. And then at the end, we'll just call super.update. That's all we need to do in order to update our model constants buffer. Let's just create a function. I'm going to create a private func. This is going to be update model constants right there. And then I'm going to put all of this logic in here so that it's not too, so it kind of, this will update our model constants buffer. And then I'm going to call from up here, update model constants buffer. So the first thing it's going to do is update all of our model constants, and then we can do other logic right here. So yeah, that's how we create our model constants instance game object. The next thing we have to deal with is the rendering, and that will come in just a second. But yeah, let's do that right now. So first thing we'll need to do is, like I said in the description, we need to set our render pipeline state. Now, if I say render command encoder dot set render pipeline state to our render pipeline state library dot pipeline state that we've created, I only have basic. Okay, basic doesn't actually deal with instancing. There's a very special operator for instancing. So for right now, just so it doesn't break, I'm gonna type basic, but we need to create an entirely new vertex function in our shaders to do instance rendering. And it's very easy, just like one parameter we'll need to add. And so if we go to our myshaders.metal and just copy the vertex function, okay, it's gonna be very similar. And I'm gonna paste it right underneath. So I have this basic vertex shader, and then underneath it, I'm gonna have instanced vertex shader. So very similar. If I build, everything works just fine. The only difference is, let's clean this up. The only difference is I'm gonna add one more parameter. And this parameter is going to be a const. No, let's not make it a const. We'll make it a uint instance ID, and then we'll pass in the attribute of instance ID. Cool. So now And also, sorry, we're passing in a reference to model constants. So this is just one model constant. What we actually need is a pointer. So this is like an array of model constants. So if I save and build, it's gonna break because right now model constants is an array and this is trying to grab one value. So what we need to do is we need to just grab the model constant of this array at the instance ID. So it's gonna iterate over these one at a time. We just need to grab that model constants in the array of the instance ID, and that's really simple. So right here, what I'll do is I'll just create a new object of model constants, and I'll call it model constant, which will be just singular equals model constants at instance ID. See that? So we're gonna grab from the array of the instance ID, and it'll automatically do this for you. You don't need to worry about it. And then we'll just remove the S off model constants.model matrix. If I build, everything works just fine. Just fine. Right now we have no way of using this vertex shader. It's not plugged in anywhere. So what we need to do is we need to add it to our shader library. So the first thing I'm going to do is I'm going to go to our shader library. We're going to create a new case for our vertex shader called case instanced. Down here in our vertex shaders, we're going to want to add a new vertex shader also. So upon generation, we're going to create our instanced shader right there. And instead of basic vertex shader as the value, I want an instanced vertex shader. Now that doesn't exist yet. So let's go down here, just copy that basic vertex shader right underneath it, paste it, type instanced vertex shader. Change this to instanced. Just a lot of typing of instances. Instanced vertex shader. Now this name, remember that name needs to match our shader name. So what you could do is you just go in here to your vertex shader in the shaders.metal, go back to your shader library, and just copy and paste it so that you're sure that it's exactly the same spelling. Now we have our shader linked up, but our render pipeline state isn't actually using that the shader yet. As of right now, we're using basic, and if we go to our render pipeline state library, it's using the descriptor of basic. If we go to the descriptor library, descriptor of basic is using the shader of basic, and we don't want that. We need to create a new render pipeline descriptor. So I'm going to copy the render pipeline descriptor, paste it down here, and pull it up a little bit. I'm going to call it the instanced render pipeline descriptor. I'm going to use the vertex function of instanced that we just created. It should work just fine. And now when we create this render pipeline descriptor library, we'll need to do exactly the same thing. Is create the instanced and then just add it when we start up our application. So instanced. I'm typing instanced a lot. Let's go, oops, instanced. So now we have our instance render pipeline descriptor tied up to instance, which uses our instanced vertex shader, and you can use an instance fragment shader, but really it's just going to be the basic one. It's going to be very similar. So we're not going to even do that. We're just updating the vertex shader. Now let's create our render pipeline state. Up at the top, we're going to need to create case instanced. Aren't you glad we built this library so it's really easy to add this stuff? Instanced, and then we'll need to create our instanced pipeline state. And this should be the last step that we have to actually do. Instanced render pipeline state. Instanced render pipeline state, and the last thing, render pipeline state equals make render pipeline state descriptor dot instanced. Boom! Now we have an instance render pipeline state to be done inside our game object. So if we go back to our instance game object, down here, we're going to use the render pipeline state library of .instanced. Man, that's how you create a new shader, by the way. And it's a little difficult, but once you've done enough shaders, it's very easy. But we've created an entirely new render pipeline state, which is instance. That's awesome. Next thing we're going to need to do, let's just go back to our game object. Our game object render is very similar, so I'm just going to copy everything under render pipeline state, copy that, and just paste it into our instance game object. Now, it will be different. It will definitely be different. And one of the ways that it's different is that we set the depth stencil state. Cool. We need that. We still need that. Vertex shader. Our mesh.vertex shader. Vertex buffer. Well, we actually never generated our mesh. So let's do that. Up at the top in it, we have mesh type. We need a private variable, private var called mesh. And the mesh is going to be our vertex data, right? So let's go self.mesh equals mesh library dot mesh of dot, well, whatever mesh we passed in. So mesh type. Boom. Mesh type. Mesh. We have a mesh. Down here, technically we can do this. Mesh.vertex count, mesh.vertex buffer. Instead of setting model constants of the reference, we want to actually set a buffer. Set vertex buffer, because we created our model constants buffer. Offset of 0, index of 2, just like it was before. Like if we go back here, see the index is 2. We're doing the same thing, just a pointer now. Same stuff. All right, so everything is the same. It looks very similar. We're passing in this constants buffer. The only thing we need now is our instance count. Now we're gonna change up the code. We're gonna clean it up a little bit because mesh.vertex count, mesh.vertex buffer, the rendering of this is always gonna be the same. We're always gonna set it at index 0, and we're always going to be drawing the primitives based on different things. So what I'm gonna do is I'm gonna move these two functions. So I'm gonna take render command encoder, I'm gonna cut that, put it above the draw primitives, and I'm gonna take these two and I'm gonna take them into mesh library. Okay, so let's cut those. So I'm gonna cut those two functions. We're gonna come back here, but go to the mesh library. In the mesh library, I'm gonna create a new func under custom mesh called draw primitives. And what that's going to do is these two things. Because we have the mesh in stuff in here, we can just call draw primitives. This isn't very flexible because we'll want draw primitives on every single one of our different types of meshes. So let's go to the protocol mesh and just generate this as a function. So func draw primitives. And actually we need to pass in the render command encoder. Render command encoder. So I'm gonna take this parameter and I'm gonna shove it into the draw primitives that I've already created. And boom, get rid of this mesh vertex count, mesh vertex buffer, pretty it up a little bit. Oops, what's going on? I put too many parens. Drop this down, drop this down. All right, pretty cool, huh? Custom mesh now has draw primitives. Everything should work just fine. So if I go back to my, let's say game object class, let's go to game object. Game object, we can remove mesh.vertex buffer. And we can remove this render command encoder.draw primitives. And we can say mesh.draw primitives. Just pass in the render command encoder. And we can do the same thing with that down here in instance game object. See, same exact thing, except this one's private. Probably should make the other one private too, but that's okay. Now we're calling mesh.draw primitives, render command encoder, and it's gonna do the exact same thing it was doing on here, except since we're doing it every time, we may as well just consolidate that into one function. And yeah, let's just press play to make sure that it's still rendering at 3 frames per second. It's still rendering, everything's the same. So drawing primitives is still working. However, we're not instancing it yet, right? Because we actually haven't created, one, we haven't created our instance game object in our scene. 2, we haven't actually set the instance count. So there's one more thing that we have to take into consideration. So back in mesh library, render command encoder.draw primitives, there's one more. If we were to just kind of comment this one out, go down, type render command encoder.draw primitives, you'll see that there's a bunch of different kinds of draw primitives. And one of those has an instance count. You see right there. So draw primitives type, same exact parameters, except now we have instance count. So if I go here, 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 I could hard code that to 1, really. If I'm only drawing one primitive, we don't even need, we can use a regular vertex buffer. It's when it comes to 2 and 3 and 4 that we're actually gonna need to keep track of the instance count. But I can create those same exact parameters. Vertex start 0, vertex count is vertex count. Same exact things, but now I have an instance count. So let's create one more function that every single mesh will be able to use, called func set instance count. And that will take in a count variable, like so. And I can delete this little code right there. Under create buffers, I can go func set instance count, self dot, well, we need an instance count on our custom mesh, var instance count int equals 0. We'll just kind of instantiate it to 0. And I can say self dot instance count equals count. And we can use this instance count now down here in instance count. This is a lot easier than I'm probably making it seem. It's not as bad as you think. Just do it a couple times and you'll get it down. But now that we can set the instance count of our custom mesh and it will automatically render the amount of instances, we can go to our instance game object class, and right when we're creating our mesh, we can say mesh, well, self dot underscore mesh dot set instance count to instance count. Now our mesh knows that when we draw primitives, the instance count is whatever we passed in, and it will draw that many instances. Wow, right? We are done with the backend code. We now can render instances, I think. So what we're gonna do next is we're gonna create one more object in game objects, and I'm gonna call that cube collection. Because really, like what we're rendering right now in our sandbox scene, this shouldn't be added individually. We need one collection, one instance, right? So I've created something pretty gnarly. This is our cube collection. First of all, I've added metal kit. The second thing I did is I went back to our instance game object and I made nodes internal so that any object that inherits from instance game object can use the nodes class. So back in cube collection down here, like you can see, I called nodes. It's not private, but it's not public, which is good. So let's talk about what I've done. So for the initializer, I basically pass in how many cubes wide I want it to be, how many cubes high, and how many back, right? So what kind of a shape are we looking at? And then I just initialized our cube collection because the instance game object takes in an initializer that takes a mesh type and instance count. And since I know basic algebra and how to get the volume of a cube, all you have to do is cubes wide times cubes high times cubes back to get the number of nodes we're gonna actually need in this thing. And if we do 20, like we were doing before, that's 8,000. So this is gonna come out to about 8,000. And just to prove that to you, I printed it out here. What cubes wide times cubes high times cubes back. That'll print out the cube count. The second thing I've done is I've kind of just set these values right here so that I can reuse them down in our update statement. And then I've just set the color of our material to just a random color. So it's gonna be different every single time. We might need to press play a few times to get a good color, but that's just gonna set a random color. You can set that to a static color if you want to. So that's the initializer. Down here in the update function, what I've done is I'm incrementing the time as time goes on. I have let half wide, half back. So this will basically give me from negative this to positive this. So it's just basically gonna have it and then make it so that I can center it very easily without having to move everything around. So this will just get like from -5 to +5. If I pass in 10, -5 to +5, and 0 is right in the middle. See? So I'm keeping track of the index right here. I'm doing basically, so if you look at this function, 4y, 4x, 4z, what I'm doing is I'm doing exactly what we're doing inside of our sandbox scene as of right now with y, x, and z, except now I'm taking in half wide, 2 half high by 1. So this is how you actually stride over a float. It's kind of weird. And then, so I'm basically creating a Y position, an X position, and a Z position. And I'm multiplying that times a gap. So the spacing of the cubes together. And the reason I put this in the update statement is because I want it to change over time. And the way I've done that is by passing in the cosine of time divided by 2. So it's gonna this will slow it down a little bit. But time right here is going to be increasing on the update statement. And the cosine of time will be going from 0 to 1. I think that's cosine. Hope that's the bounds. If it's not, it's not. I think it's 0 to 1. And then dividing it by 2, so it's just going to slow it down. And then I'm going to multiply that by 10, so it gets really big. Okay, so that's just like the gap of each of from cube to cube. And then I'm increasing the index by 1 down here in the Z because I'm iterating over these nodes. So I grab the node at the index and I set the position X, position Y, based on whatever I want. So I've kind of just created this function. I played around with it for a little while. And then I'm calling super.update down here. So if you want to play with this code, you're more than welcome. But yes, this right here gives us our new cube collection class. So let's go and use it. Back in our sandbox scene, as opposed to going for blah, 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 I'm going to delete add cubes, all that logic. I can go let cube collection equal, let's say a cube collection. And that's going to take in the parameters of, boom, cubes wide. Okay, I want 20. Cubes high, 20. Cubes back, 20. Okay. Also, my math was wrong. Just occurred to me my math was wrong on the original one. That was a lot bigger. That was like going -20 to +20. That's 40, if you think about it. I'm only doing 20 here. So it's a lot different. If I do 40, this is probably gonna break. I think 20 is probably the max. So no matter what, this is wrong. Actually, let's go back and we're gonna change this up just a little bit so that we can see what the difference would be if, boom, boom, boom. Let's see if it actually runs. It might run super smooth, who knows, right? So let's make it 20 on every single one of those in the old way. This is the old way, okay? Obviously it's gonna break because something's bad. So actually we have a problem here because what's happening is my instance count, just occurred to me, is set to 0. We need to set that to 1 initially. And then we're press play because it can't have an instance count of 0. Render nothing, please. Right now. Look at that. It's actually running pretty good. It's at 23 frames per second. Not too bad. Okay? Not too bad. So 24 frames per second, but that's it. We've maxed out at 8,000 objects. That's 8,000, by the way. So if we go back to our sandbox scene, now we're at 20. Remember, we're at 23 frames per second. And let's just comment this out. So this is the old way. Let's create a new way, func. So let cube collection equal cube collection. Pass in the params of 20 by 20 by 20. And we'll just add child cube collection. Look at that, we've only added one child, but we have 20 by 20 by 20. You see that? That's crazy. Now, if I press play, we should get a pretty cool effect, hopefully. If we don't, I'll fix it. Oh, boom! Look at that. Whoa! That's awesome. So yeah, basically now if I go to my rendering right here, looks like we're rocking 59, 58 frames per second. It's probably running slow right now because of my screen flow, to be perfectly honest. But you see, we've upped our frames per second. And when I say screen flow, I mean like my recording software. I've upped my frames per second to be awesome. And now we have these really cool cubes rendering on the scene. And what's also cool is, say we want multiple different types of them. Well, what we could do is, one, we're gonna shrink this in half because I think we just don't want to render that much. I don't have the best GPU. It's an okay GPU. If you get an external GPU, it's probably a lot better. So I'm gonna add 2 collections. Now, okay. Actually, you know what? Before I do this, let's talk a little bit about grouping, okay? So if I wanted to go and make an update statement, func update down here, super.update. If I wanted to do this, I would have to do something along the lines of, override, sorry. So if I wanted to rotate, let's say rotate my entire cube collection, okay? So it's all working as one group together, right? I want to be able to just create this up at the top, var cube collection, instantiate it right here, delete all this old nastiness. So I have this cube collection, I've instantiated it, and I've added it. Now I actually want to rotate it. So cube collection dot rotation dot z plus equals delta time. What do you expect to happen right now? Because I'm thinking it's not going to work, and there's a really good reason as to why it doesn't work. See, it's not rotating. Our whole group is not rotating. It's also shifted off into like, oh, it goes back and forth. Interesting. Okay, so that's just my math being wrong. But that actually doesn't matter too much because let's put this back to 20. You can play with that later. Obviously, I didn't do any testing. But if we update and we go cube rotation, it's not going to update the entire group. So what we need to do, actually, is go back into our instance game object, go to our update model constants buffer. Now, remember, linear algebra is basically like a combination of linear functions. Okay, so if I multiply one matrix by another matrix, I get another matrix. Like model matrix times view matrix equals model view matrix. What we need is our nodes to rotate based on the parent node, which is this class. So every node needs to rotate with relation to my own class. So pointer.pointy.model matrix equals node model matrix is wrong because that's only going to give it the rotation relative to the node. I need it to both the node and my matrix. So what I'm going to do is I'm going to use this function matrix multiply. Okay, I'm going to multiply the node's model matrix by my model matrix. And what that's going to do is it's going to combine the matrices together and create a new matrix, just like the model view matrix. Okay, so now if I press play, I'm thinking the whole entire thing is going to be rotating. And I'm wrong. Why am I wrong? One sec. Okay, so I spotted it. Right now, so the order of operations is very important. We need to multiply my matrix by the node's matrix because this is the parent matrix. So if you just invert self.model matrix times node.model matrix, you should get a different output. So let's press play, invert those guys, my bad. And see our entire object is rotating in space. Actually, I'm getting hypnotized a little bit, but you'll notice our entire object is rotating relative to the parent. So boom, pretty cool. But let's not stop there. I wanted to actually get into one more cool little thing, and that's going to be creating another cube collection right here, and we'll call it, we'll actually rotate both, maybe in opposite directions or whatever we want to do. We'll call this one 1. So cube collection 1, cube collection 1, cube collection 2, cube collection 2, cube collection 1 dot rotation z, copy. Cube collection 2 dot rotation z can go like negative, the opposite direction, so they'll rotate together. But I need to set cube collection 1 dot position dot let's see, x equals, let's do negative 16, and then we'll do positive 16. So we're going to shift the first collection over to the left, and then we're going to shift this collection over to the right. And so we should have 2 rotating collections of cubes off in space. And since this is 20 by 20 by 20, obviously, I mean, still 16,000 objects. What am I rocking for my RP? So I'm down to 24 frames per second. Basically what I was at when I was rendering, just the 8,000. That actually doesn't look too bad. Let's just divide this a little bit down. We'll go 10, 10, 10 for all of these. And you can play with these numbers. Your GPU is going to do different rendering. Different rendering based on, what your system can handle. But yeah, so woo! Look at that. Look at that guy. All right, so yeah, I mean, that's really cool. I'm not going to do that. I'm going to get rid of it, and I'm going to go back to the 20 by 20 by 20 just because it looks cool for the end episode, blah, blah, blah stuff, you know? Like, so I can be like, this is what's going to happen at the end of the episode. Got to do that. Get pumped up about it. And let's see it. Last but not least. Whoa! Whoa! Oh, so I shifted it over to the left. That looks even trippier. Whoa! I don't know. I kind of like that a little more. I feel like Harry Potter going through like the room of all the magical orb things, and I want to knock them all down. Boom. I'm gonna make a better color. It's a good color. Yes. In your face. Out of your face. 8,000 objects rendering at the same time. Hit me up in Discord if you have any questions. I do not mind answering any of those. There's a lot of people in there that actually help out a lot. I really appreciate it. I asked them actually what my next episode should be, and they suggested this. I wanted to do like tessellation, probably going to be coming out pretty quick. I just wanted to do some more actual metal rendering stuff because metal is kind of complex to read through. There's not much documentation. So, but if you have any suggestions, hit them in the Discord channel. Like, subscribe, do all that jazz because I do appreciate, you know, the followers. Makes me want to make these more because I know you guys want it. And yeah, thanks for watching.